Last time we looked at magnetic forces on current carrying wires, and you might have wondered, well, what if there's no wire there? There's just a current, a bunch of charged particles moving. Would those also feel a magnetic force? And indeed they do. If we start out looking at our equation for the force on a wire, force equals IL cross B. And then if we rewrite the current as charge per time times L cross B, well, we can say that the total charge per time is the number of charged particles times the charge per particle over time. And L, we can say, is velocity times time. We'll have those vectors still being crossed. The times will cancel out, and so we get NQ times V cross B. And if we just find the force on a single particle, that's going to get rid of the N. So the force per particle, or F over N, is going to be QV cross B, and a lot of times we just leave that N off and we think about the force on a particle equal to QV cross B, and again we can rewrite that as QVB sine theta if we're just interested in the magnitude, where theta is the angle between the velocity and the magnetic field. So you might have wondered what this picture is for. Well, if there's a charged particle coming in this direction, you can use a right-hand rule again. So you'd have your fingers pointing this way, your palm pointing to the right, and then the force would be up. And if it's a negative charge, essentially you can use your left hand if you'd like, or just do a right-hand rule and then remember to reverse it at the end. This picture, the perspective's kind of weird, but I'll show you some more examples of the deflection of charged particles in magnetic fields. So here are a number of examples of different particles, and let's say we shot a bunch of particles in this magnetic field and they traced out these different paths. What could we tell about these different particles? Well, this particle right here, since it doesn't get deflected at all, we would know that it has zero charge. These two particles would have the same charge, actually these three, and A would have opposite charge, and if we think about it for a minute we can figure out which is which. Let's take A just for fun. So if we put our fingers in the direction of that velocity, now the magnetic field, these crosses mean that it's going into the page, so if we point our palm into the page, and that's the velocity, our thumb would be pointing to the right, which would mean a positive charge would feel a force to the right, which means this guy is negative and all of the other ones are positive. Now the difference between C and B could be that they have different amounts of charge, or it could be that they're the exact same particle but with different velocities. And so that will cause them to trace out different arcs. Okay. A couple of important things to think about with this new equation of QV cross B. What happens to a charged particle when it's placed at rest in a magnetic field? This one's pretty easy. If we've got QV cross B, if V is 0, then you've got Q times 0 cross B. It doesn't matter what any of these other things are, this is going to be 0. So you can't get a charged particle moving that's initially at rest with a magnetic field. Also, could you stop a charged particle with a magnetic field? No. If you look at QV cross B, what you notice is the force is the cross product of the velocity and the field, and that means it's always going to be perpendicular to the velocity. So you will never be able to change the speed of a particle with a magnetic field. You can only change the direction. So another implication of that is that the work done by the magnetic field is always going to be 0, because the change in kinetic energy has to be 0. So magnetic fields cannot do work. Alright, now let's look a little closer at these particles in magnetic fields. If you have a particle cruising along and then you turn a magnetic field on, that is going to cause this force that's perpendicular to the velocity, and we might recognize that as a central force or a centripetal force, and that results in circular motion. So if we do a little bit of analysis here, if we say that our magnetic force is our centripetal force, and if we just take the magnitude of the magnetic force, it's going to be QVB. And the centripetal force is mv squared over r. One of the v's will cancel out, and we can figure out the radius of the circle that a particle a charged particle in a magnetic field will trace out is going to be mv over qb. So there is a nice little expression that you will be using later. And we can use all of our equations for circular motion. For instance, the period of this orbit here in general is 2 pi r over v. And if we plug in that for r, we're going to get 2 pi mv over qb all over v. So the v's are going to cancel out, and we end up with 2 pi m over qb. So the period is independent of the velocity and the radius of the circle. Okay, and then the frequency is just the inverse of the period. Easy enough, qb over 2 pi m. Alright, moving right along. If we have a charged particle that enters a magnetic field not perpendicular to it, because if it's perpendicular it will go in a circle like we just looked at. If it enters parallel to it, then it will not be deflected at all. It will feel no force. It will just continue straight on. But if it enters at an angle like this, then you have a vertical and a horizontal component. And so essentially both of these things happen. The vertical component, or the component perpendicular to the B field, is going to cause it to go in a circle, but then the horizontal component is going to cause it to move at a constant speed to the right, and so you'll get a nice spiral corkscrew pattern. And this is actually what happens in the Earth's magnetic field. We get charged particles from the sun, what we call the solar wind, and those get caught in the Earth's magnetic field. Now the atmosphere doesn't extend nearly as far as the magnetic field, so these things move pretty freely out here where there's no atmosphere, spiraling around those lines of a magnetic field. And then the field lines enter at the magnetic north and south poles, and so that causes these particles to spiral in towards the Earth when they get close to the poles. And that's when they collide with the atmosphere, and they impart some energy to the particles in the atmosphere, which then give that energy back as light, and voila, northern lights, southern lights, and all of those fun things. Alright, last thing is what we call a velocity selector. In a lot of experiments, it is very useful to have a charged particle going at a specific speed, or not a single one, but to have a whole stream of particles at a specific speed. And so what we can do is we can, if you have a slit like this, usually to get charged particles you can like heat up a piece of metal and they will just kind of start spewing off of it. And so if you have a slit here, that's going to block all the particles that are going in random directions. So you'll just get particles that are moving more or less in this direction, but some might be going faster and some might be going slower. But if you set up an ingenious little device that has an electric field, so you have charged plates here, as well as a magnetic field, what can happen then is you can select just the perfect velocity to go straight. Essentially, the electric field, if this is a positive charge, that's going to cause it to curve down, and the magnetic field, you can do V cross B, so V is going this way, the B field is in, so that's going to cause a force going up. And so if you're going too fast, then the magnetic force is going to be too strong and you'll deflect up here. If you're going too slow, the magnetic force is going to be too weak and you'll deflect right here. But if you go just the right speed, you can have these two forces balanced with each other and you will just follow a nice straight line. So only those that are going just the right speed will come out here. And we can pretty simply solve for that speed. If we want the magnetic force to equal the electric force so that we go in a straight line, just taking the magnitudes, because the velocity is perpendicular to the magnetic field anyway. So you're going to have QVB equals QE, and the Q's cancel out, and so the velocity you want you can get by adjusting the ratio of your electric field to your magnetic field such that that equals the velocity you want to get. And this will work for any magnitude of charge. It also works for either sign of charge, because if you have negative charges, it swaps both the electric and the magnetic forces, so this still holds. Alright, now next video we'll do a few calculations.